context of electronics. We know of conductors, which are familiar to us. Most metals are very good conductors. They contain a large number of free electrons so that they can participate in conduction. We have great insulators like polythene or rubber or ceramic, which contain electrons, which contain charges, but these are all bound charges. They can't move inside the material. They cannot contribute to conduction. Now, some kind of a gray area exists between these two extremes. We have materials which do not have the same insulation properties as insulators, but are also not as conductive as conductors. This little gray area in between belongs to a separate class of materials which we call semiconductors, or more accurately, intrinsic semiconductors. So what do these intrinsic semiconductors look like? Well, if you look at the atomic level at these materials, you will notice that the atoms in these materials will be arranged in regular patterns and they are sharing electrons with their neighboring atoms. This is not like an ionic solid where you have a positively charged ion and a negatively charged ion and they are attracting each other due to electrostatic forces. This is a different arrangement. For example, if you look at the two most common semiconductor materials, that is silicon or germanium, you will notice that each atom in this system is sharing 4 electrons with the adjacent atoms. So you will notice that here we have a sharing arrangement with the adjacent atoms. Please note, these electrons are not completely removed from one atom and given to the other. This is not an ionic bond. This is something that we call a covalent bond, which involves the sharing of electrons. Now, because these materials have a valency of 4, that is, each atom needs to share 4 electrons with the neighboring atom to maintain maximum stability, we can say that the cores of these atoms, or effectively the nuclei of these atoms, are displaying a charge of +4. So we can write that these nuclei are displaying a charge of +4. This will not be readily apparent because overall the entire material is still electrically neutral. Nevertheless, the effect still exists. Now, if this material was sitting at absolute zero, at 0 Kelvin, there is no thermal energy anywhere in the system, the electrons really have no energy to leave their parent atoms or these bonds. So, at 0 Kelvin, there are no free charges in the system. These materials, these intrinsic semiconductors, are behaving exactly like great insulators. There are simply no charge carriers which can contribute to conduction. But if you were to increase the temperature above 0 Kelvin, so if you start giving thermal energy to this material, to this system, a small fraction of electrons will start vibrating inside those covalent bonds because of the transfer of thermal energy to them, and out of that a small fraction again of electrons will gain enough energy to jump out of their parent bond and leave. So these electrons will start moving inside the material. So these are what we will call free electrons. Now, if an electron is moving out of a bond position, it is creating a vacancy, and this vacancy is what we call a hole. So if this electron here has left, now we have created a vacancy here, and this vacancy is what we call a hole. Now, a hole is not a positive charge because it is technically the absence of an electron, but because the nucleus is positively charged, a hole behaves as if it is a unit positive charge. If you were to apply an electrical field to this material, you would notice that the electrons are starting to move towards the positive side of the field. So the electrons start drifting to the positive end of the field, while these holes are shifting towards the negative side of the field. Now, this may raise a question in your mind, that holes are vacancies caused by the movement of electrons out of these bonds. So unless the entire atom starts moving, how can a hole start moving? And what is interesting here is what is actually happening is that as the electrons are drifting in one direction, they are uncovering these covalent bonds. So it seems as if while the electron is moving towards one side, the holes are drifting towards the opposite side. What you are actually observing is bonds being uncovered due to the movement of electrons from one side to the other. Another thing to understand here is that the total current inside this material will be the combination of the hole current and the electron current. So we can say that the total current in this system in the presence of an electrical field, that is capital I, will be equal to IE plus IH, where IE is the electron current and IH is the hole current. As you keep on increasing the temperature of this material, more electrons will gain enough thermal energy to break away from their covalent bonds. More electrons are formed, more holes are formed, and the formation of these electron hole pairs is what we call simply generation. Now, the process is not entirely one-sided because at any given temperature, there is a given number of free electrons inside a material, there is a given number of holes in a material, and that number remains stable because as more electron hole pairs are formed, somewhere else in the material, electrons are also losing energy to their surroundings and drifting back inside the covalent bonds that they had left. So when a hole and an electron recombine, when the vacancy is again filled by an electron around an atom, we call this process a recombination. So the formation of a free electron and a hole pair is known as generation, while the recombining of these electrons and holes again to form a stable covalent bond is what we call recombination. And the total amount of free charges that exist within a semiconductor material, within an intrinsic semiconductor, depends on the temperature, which will state what will be the equilibrium point between the generation of these carriers and the recombination of these carriers. We can also look at the situation from the standpoint of the individual energies of these electron hole pairs. We can look at it in this form. Let's try to create an energy band diagram for the system. What is an energy band? An energy band is a graphical representation of all charge carriers inside a material which are having similar or identical energies. So we can create two bands here. We can create two regions here. This is one region and this is the other region. And these two regions are based on their energy levels. The white region at the bottom is a region of lower energy. So we are charting out the energies here. Energy is increasing as we move up. So this lower region is a low energy region. So this is what we call the valence band. This comes to be known as the valence band. So this region is what is occupied by all those electrons which are sitting safely inside their covalent bonds. This is the low energy region. Now, when you apply energy to the system, it can be in the form of heat, it can be in the form of light. The mechanisms vary. The electrons sitting here in this region, or at least some of those electrons, will gain enough energy to migrate into the upper region, the higher energy region. And this region of high energy is known as the conduction band. This is what we know as the conduction band. So what happens to this region, the valence band, when the electrons leave it? Well, when the electrons leave this region, what we observe is that we have vacancies here. We have created vacancies here. And these vacancies are what we call the holes. So this is a way of visualizing what happens when energy is gained by an intrinsic semiconductor. The electrons gain energy and they break away from their covalent bonds, creating vacancies which behave like positive charges, which we call holes. So under the influence of an electrical field, the free electrons will drift towards the positive end of the field. the holes which behave as positive charges will drift towards the negative end of the field, and the total current generated due to these electrons and these holes will be the net current in this particular system. We are now going to understand what happens if we add impurities into these pure materials. How do they affect the crystal structure? How do they affect the number of free charge carriers? And how we can make these intrinsic semiconductors more useful by the addition of these impurities.
Manorama Horizon. Learning made simple.